Hello guys, welcome to my channel Knowledge Unlimited. In this video, I am going to explain one more interesting example, adding the skew analysis as well. So if you see right, the question is to find the maximum operational frequency here. And there are two flip-flops given, flip-flop 1 and flip-flop 2. Flip-flop 1 has a setup time of 50 picoseconds, hold time of 50 picoseconds, and the propagation delay of 100 picoseconds. Whereas flip-flop 2 has a setup time of 100 picoseconds, hold time of 50 picoseconds, and the propagation delay of 100 picoseconds. And the combinational logic here has min time of 200 picoseconds and the max time of 800 picoseconds. And here if you see right in the clock path, there are two combo logics had, which is 20 nanoseconds each. Now the question is to find the maximum operational frequency. Now very simple thing here. If you see right, this is the path that we are trying to analyze. And in the setup time analysis, we need to use the max delay. So let's use 800 picoseconds here. And you're all aware of the setup time equation, and the time period that you want to determine the max frequency depends on the setup time equation and all. If you're not sure about it, please go and watch my earlier tutorials. So in this, if you recollect, both flop 1 and flop 2 are getting the clock with the same delay of 20 nanoseconds. So we can ignore that, to be frank. So now the equation here itself is T clock should be greater than or equal to the propagation delay, that is 100 picoseconds, plus the max delay here, that is 800 picoseconds, plus the setup time of second flip-flop, that is the capture flip-flop, that is again 100 picoseconds. So if you add all these three, T clock should be greater than or equal to 1000 picoseconds. So the max frequency equal to 1 by minimum T minimum. This is the minimum clock period, right? Which is 1 by 1000 picoseconds, and this is nothing but 10 power 12 by 10 cube, 1 gigahertz. So this is the maximum operational frequency. Now this is so simple, right? What's there in this example to even think? It's very straightforward. So let's tweak this question a little, and rather than adding like this here delays, let me erase these two paths. Now the same clock I'm keeping in a different way. Okay, so I'll add here a delay of 100 picoseconds, and here I'll write clock, because there are 20 nanoseconds, or sorry, 20 picoseconds and 20 picoseconds on both sides. Because they are same, I'm just removing them and I'm adding a combo logic here of 100 picoseconds. Now if you see right, for the flop 2 it's coming early, whereas for flip flop 1 it's going with an additional delay of 100 picoseconds. Now this is the normal clock that is present. Now with this 100 picoseconds, I just redrawn it with a delay of 100 picoseconds here. This is 100 picoseconds. So if you see here, everywhere the moment is 100 picoseconds. This is 100 picoseconds. Now what's interesting here is the first clock waveform is what the clock going here, where the second one is the clock at this point. Okay. So what's happening really here is the flip-flop 1 is getting clock very late than the flip-flop 2. So now the setup time analysis here, or the setup time equation, how you can write is, your window, your new window will be from here to here, because this is at the second flop, right? And this is at the first flop. Now this is your window. So let me change the color. So this is your new window here. But this is what the clock period ideally is, T clock period. But here you're having an additional, if you look from here to here, you're getting 100 picoseconds less than the normal clock period. So the equation now will change to, so ideally this is what your T clock, right? But you're having 100 picoseconds less. Here this is 100 picoseconds less, or here it is 100 picoseconds less. So it's like T clock minus 100 picoseconds should be greater than or equal to the same. What the same? Like 100 picoseconds of propagation delay plus max of 800 picoseconds plus the setup time of 100 picoseconds of flip-flop 2 here. So it's like T clock should be greater than or equal to, this is 1000 picoseconds plus this 100 will go that side. So your T clock now should be greater than or equal to 1100 picoseconds. And from here you can get the Fmax by 1 by 1100 picoseconds. I don't want to do this calculation. You guys are well aware how to do. You guys just determine. So what I just want to say here is, this simple example will give us a knowledge, right, in the PD analysis and all, how the even clock distribution is important. So if the clock going to the flop 1 is delayed by certain time than the flop 2, you can see, right, your maximum operational frequency is reduced a lot. Like earlier it's 1 gigahertz, but now it will be less than 1 gigahertz. So with uneven clock distribution, your circuit that you are going to design will operate at less frequency, so that you are reducing the performance of it indirectly. And here also you can see, because I always believe that than using the formulas directly and all, if you try to analyze by looking at the waveform and the time period and all, the intuition will be more clear and the knowledge that you'll gain will be more broader. Okay, so here it's very simple, though it's look little confusing here. The clock period still is from this edge to this edge, but here like you have little less window now to accommodate the combinational logic delay, the entire combinational logic delay, propagation delay, setup time and all. So obviously your clock period will increase than the previous case. So that's how it's simple to analyze in that aspect. More questions and all you can solve on your own. I hope you guys learned something new in this video. Stay tuned and subscribe to my channel for more videos and more beautiful examples. See you soon.